Okay, I'm Kurt Miller, Director of Engineering, Suwanee Valley Electric.
Yeah, I'm Trevor Touchton, Manager of Power Technical Systems, also Suwanee Valley.
Okay, we're gonna tell a story of a success distribution automation project. So we'll go over what FLISR is, the results of our project, some of the decisions and the discussions that went into making the project happen, some of the lessons we learned during the project, and obviously chime in anytime you got a question. We'll try to answer it. We're located on the Georgia border here in Florida, and we serve these 4 counties, probably about 3 hours north of here. So FLISR, there it is. It's fault location, isolation, and service restoration. It's what we do. If you didn't have automation, you'd be doing the same thing. Since it's automated, we call it FLISR. So, are you a good candidate? What we think is if you're overhead and you've got a lot of trees, like we do, 80-foot trees up and down your 20-foot right-of-ways, you're probably a pretty good candidate, particularly if you're in the southeast. Technical staff, technology doesn't always mean less people. You need more technical people. You're going to need it in the build-out phase and the support after. You're going to have to train the folks in the control center. You're going to have to train linemen, etc. Will you need to upgrade your software or not? There's different platforms there. You got OMS, GIS, SCADA, AMI. Comfort with automation at the co-op. This really speaks to the operational folks. They're concerned about safety. They're concerned, about somebody closing something in on them while they're restoring power. At SVEC, we operate full auto in our FLISR, and our control center is at times unmanned, so the system just operates. We have to restore it, so we have an on-call dispatcher operator can remotely restore it, or they come into the control center. So we'll move on our starting point. We have 13 substations, 42 feeders, 3,200 miles of primary line, serve about 27,000 meters. Our reliability numbers from 2010 to 2016, you can see there the SAIDI average was 277 minutes, our CADI was 85 minutes. Reliability plan that was put together, was basically reduce outages, and the only way you do that is, improve your right-of-way and reduce the outage size, and that's where FLISR comes in. So our results this would be from 17 to 2021. We basically had a 32% reduction, or 89 minutes of SAIDI reduction. And this was, filtering out what we call major event days. This is just your all other or controllables. So we attributed 57 minutes to that. And when you go back and look at all the numbers to FLISR or feeder outages, our CADI went down a little bit, about 7%, and about 100% of those CADI savings came from FLISR. And the takeaways, is it effective for SAIDI reduction? There's no doubt it is. I mean, you take an outage that has 1,000 people, and a minute later, it's down to 500 people. So it's pretty obvious. We spent about $2.5 million, reduced the SAIDI 57 minutes, so we kind of estimated it cost us $44,000 per minute for that reduction. Would we do it again? Would our board do it again? Would our management do it again? Yes, it's been a very positive thing in our territory. Our members, our consumers have commented on how the reliability has improved over that period. So we'd definitely engage in doing that again. It's worked out really well for us. So these are some graphical results. You see a downward line there in SAIDI, very positive. Outages, which are really driven by weather and right-of-ways, really kind of leveled, and Katie's gone down a little bit. FLISR started rollout 2016, completed in 2018. And there's some tabular results of the numbers. Any questions on the results or anything before we move into the project and what it took to make it all happen?
It was your 6-year rolling, then compared to that 1 year with FLISR?
So the averages are just a 6-year average, not a rolling average. But FLISR was complete in 2018, so from there on we were 100% fully deployed on 44 feeders or something like that. All right, well, I'm going to hand it over to Trevor.
Yeah, thank you. So go over the project. I don't know how many of you are thinking about doing a project like this, but there's multiple layers that go into building the FLISR system. The very first thing, anytime you want to do FLISR, is you got to have communication. If you can't talk to those devices in the field, there's no sense in thinking about doing FLISR because you can't get any signals out to them. This is our territory. You may be able to see these green lines at the bottom, red lines at the top, and there's some hourglass figures. So we had a microwave ring on the south. We had a double microwave ring at the top. You can see to give us extra support. The hourglass is really a point to multi-point. We had some other towers that were closer to our main headquarters. So when we started evaluating this, we looked at fiber. Fiber was too expensive. Microwave and towers was more economical. And we didn't want to go fully cellular because we wanted to be able to control it. If a hurricane comes through, we want to be the one to get it back up and running if we need to. We don't want to depend on somebody else to be their last priority. So the other decision after you decide that is, you've got to get a backhaul from your stations. Well, then you also have to get your backhaul from your endpoints. We went with a 900 megahertz radio system and some cellular there. We took the risk on a few devices. You lose them or you can't get coverage. But essentially what we did is every blue dot you see here, these purple dots, we did a 900 megahertz omnidirectional antenna there. We went out from this area. We could pick up remotes around each tower. And what that did is that allowed us to communicate to our downline devices back to the station and microwave back to the office. And the reason we did this type of communication is because we wanted to do a centralized control for our FLISR. We didn't want to do local control at every substation that maybe has to be programmed here, and then you forget something, you have to program something different somewhere else, and you make a change year 3, or you got to go update everything we did year 1 and 2, or you have a different scheme running. We wanted it to be simple for our linemen, simple for our operators. Everything's in one place. You make a change, it's global for the whole system. And then also, your time of install for us, we did the green year 1, we did the middle of our system year 2, we did the top year 3. And the other portion you also want to remember when you're thinking communications is how fast do you want it? Do you want to have sub-second switching? You want to switch on that first fault? Do you want to switch after everything is normalized and locked out? Or you just want to switch at 5-10 minutes later that may change your communication speeds you need. And then you also, after you build this system, we talked about there's some technical staff. You're going to need people that can climb towers and deal with when lightning strikes those towers and you're working in your substation to fix lightning damage. So in Florida, we do experience some of that. After you have your communications decided and you're rolling communications out, you got to pick your device in the field. We decided on our co-op we were going to go with reclosers. We have some ABB reclosers. You can use some old switches, but that's a decision you have to decide. Do you want to go install motor-operated switches or not? What we did, anywhere we needed a switch or a two-way feed, we just put a recloser, programmed it as a switch, and that way if we are feeding a different direction, we could turn that into a recloser. Everything's there, you just did another settings profile in the relay. We did a simple construction assembly. On our whole system, we have somewhere between 75 and 80 of these, and every one of them you come to looks the same. So that was with alignment in mind. We don't want you to come to one and I've never seen this before, how do I switch it? We put bypass switches above all of our reclosers in case you're there and you don't have a bucket truck. Well, what am I going to do? This recloser is damaged. Well, we can bypass it from the ground, keep it moving, keep people on as best we can. Part of that communications in your device you choose, you want to pick your protocol, be consistent across the whole system. It makes things easy if you can do a template instead of 4 different protocols, 4 different points lists. And then one of the last decisions you need to really think about is, are you going to replace or retrofit your devices? What's your switching scheme going to be once you put your devices out there outside of FLISR? I mean, these are reclosers. They're going to interrupt faults, change your coordination on your system. And then also, will you need voltage sensing on one or both sides? That may change the relay you buy, may change actually the device you buy. We went with voltage sensing on both sides because if we switch, we know if voltage made it up to the device we wanted it to backfeed to. We're not having to send anybody or ask any questions. We know it's there. So after you've picked your communications network, you've picked your devices in the field, you're kind of rolling those out, you need to be thinking in the same time, what is your function going to be for your ADMS system? How are you going to do this FLISR operation? You centralize locally, or you're going to have a device in the field that does the decisions. So we went with ACS, FLISR product. We used our GIS map that we already had. So if you don't have a GIS system, that may be hard. That's where you'd use Centrix. We also came in and we had auto fault detection, isolation, upstream restorations. What FLISR was providing us is what we were looking for. And you can do an auto or you can see a plan. You also have the ability to use load transfer switch plans during the day. If you want to pick a place on the line and say, I need to transfer this load, it'll produce a plan, and you can double check that plan. You can even execute it from the desk, move load from one feeder to another. There's an auto return to normal after everything's cleared up and the linemen have called in, the tree's gone, the wire's back to normal. You can actually click on your DAS map, return to normal plan. It pulls up the plan. You can select it and grab it, execute it as an emergency plan to return everything to normal. It also gave us a common real-time database to look for reports. We're not looking in 4 or 5 different applications to figure out how did this happen, how did we get where we're at. And there's other DMS applications in the future, like IVVC you can add in. That's where we're kind of doing that now. Outside of that, these are the following constraints that FLISR can observe. When it does those switch plans, it can do high and low voltage limits at each node. It can do thermal limits based on wire sizes in your table. It can look at loading limits on switches, breakers, make sure you're not going to overload a part of your line when you do the switching. And it's doing all this in that 45-second lockout comes in. Can we move that load or not? It looks at your source transformers, making sure you have enough capacity, and the operability of switches is part of that communication. Is this switch saying it's in local mode, or is it in remote mode? Can we use it? Is it a hotline tag? Does it have comms? all of that goes into play, and it says, oh, we have a hotline tag on this device, this feeder's off limits to backfeed. So it blocks all of this. And you can also go in, if you wanted to, you can use or ignore manual switches in these plans. You can create a plan if you have a crew out there that can get to a manual switch if you want to switch further, and it'll give you the closest switch that's on the map to operate. And then we can actually, based on our communications, we can change our data scan. So you won't, if your system is slower than you thought, you can back out this data scan, give your relays time to report in. You can collect all the data before you make a decision. And then you can also leave a delay from the time you sent a command to make sure you get confirmation the device opened or closed. So after you've got all this rolling, you've picked your FLISR application. This is the topology model that our system has. And this is a model of our communications just broken out as towers. But what you'll see is this topology model gives you system connectivity, your network model, all your device information is there from your GIS. It gives you a visual very quick. Everything's colored by feeder. When something goes out, if this feeder in green goes out, it flashes white. And then if it backfeeds a portion of it, this all turns yellow, this will turn pink, and let's say this part here is still flashing white. In our control room, really quick, you know flashing white's bad. And you can look and see here, where has it fed to, where's it open. It gives you a very quick identification of what's happening. You can also do controls on this map. So you can zoom in, the crew's done, you want to restore it, you can send your close command right from the map. Really has made us more efficient in the control center. And the last thing you got to think is, you know, is FLISR going to be standalone, or is there going to be other apps you're going to add to this map? Is there more things you can do with this later on? And then just for us, we already had a GIS map. We use NISC, and we also have MillSoft, so we can pull those models in to build this map. Whenever you're building your map, you can show different things on the map as you zoom in. For our system, as you zoom in, you pull up the map, all the SCADA controlled devices pop up first using declutter. As you zoom in further, you start to see manual devices. So when you're first looking at it, you see your SCADA points, you can open and close things. As you zoom in, you can send a guy to a switch that, hey, I'm already out there, let's zoom in and see where you're at, let's get another 200 meters on if we can. And then do a map updates with this type of system. You can do a whole entire system-wide update. You don't have to just go and update one point, but you can do it that way if you want. For us, as we were doing this process, every time we upgraded our system or added another 5 or 6 relays out in the field, we can pull them all in as a group, and we used those templates, really made things smooth. So once you have that, you got an algorithm that's going on, like I said, and these are really the 4 things the algorithm has to have. Got to have communications. I get a fault flag telling me, hey, prepare, it's time to watch. Once you get a lockout flag from a device, it's your time to perform, it's ready to go. And if you have a non-reclose, we're going to disable, we're not doing anything. This hotline tag, there's a crew out here, there's a reason we have this. So when we did these decisions, one thing we were looking for in our system was we wanted our FLISR system to capture relevant events. We want to have a standardized point list. I don't want point number 3 at this device being different than point number 3 at that device. If I have a guy that's running around trying to troubleshoot an issue with a relay, I wanted it to be very familiar, repeatable. I plug in, I read the settings. These are the settings I'm expecting. The timing sequence, that all depends on your communications and what's your lockout relay, what's your 79 cycle going to be, and how fast do you want to operate. And maybe you want to go manual mode, maybe you don't trust the system, maybe you don't run your tests and trust it. So you go manual mode, it gives you the plan, you can look at it, then execute it. We ran a lot of tests beforehand, and we were comfortable with auto, and we've ran it in auto mode, and we're getting 45-second restoration times. And then, you know, cannot run the entire system the same. For us, we have one industrial localized communication or localized area for automation. It's not on FLISR. It's one device that controls 2 breakers that feeds an industrial load. So it's actually doing its own automation in the box right there by the plant. Everything else is on this localized system or on the centralized system. So it's, You can mix and mingle, you just don't put the control points for the local system in the big system. So just recapping that, build a communications network. We had 11 new towers, and we had 4 existing towers we retrofitted. This is one of our new towers going in, 180-foot tower. Are you going to get new devices, or are you going to retrofit devices? Can your old devices do what you want to do? Do they have voltage detection? Do they not? Where are you going to place those devices? We went halfway in our meter count, not halfway in the distance. We wanted to get as many people on as we could. Do I have communications at that spot? No, I don't. So you end up moving 5 or 6 poles one way or the other until you get a good radio signal. And then this is a great place, but it's in a swamp. So you go another 4 or 5 poles. So you got to make sure your field crews can get to it to fix these devices if they do have an issue. Then you pull in your staking, construction guys, and your mapping folks, and you say, hey, we want to make this as smooth as we can. We're going to use the same assembly each time. Construction guys are going to build it the same way each time. We're not going to change our mind year 2, that we like it better this way. So it's good to have that forethought up front, get everybody in the room. And then our mapping, hey, we need these features on the map when we pull this GIS data over. Everybody kind of knows what's going on, and they start to look at it. And we were doing 20 to 25 reclosers a year out in the field. And once you deploy, we did relay testing. So we tested each relay in the field with an Omicron, made sure the relay was programmed, ready to go in the field, everything made it, all the wires were in the right spot. After that, we did a command line interface with CMI scripts on SCADA. We made fake faults. We made sure the system produced the right switch plan. Once we had a good switch plan and we liked it, we put it in auto mode. We sent guys out in the field. We bypassed our reclosers. We made a fake fault. We let SCADA pretend it was a real auto deal. The guy's sitting at the midpoint, it opens. We got a 2-way feed, it closes. Hey, this is good, that's what we want to see. After that, you do the lifelong training of your operators and your line workers. That's still continuing. That's something you guys keep in their mind. And one thing that you don't realize is sometimes they forget how they used to do it once there's something that's doing it for them. You got to remind them, hey, we used to do this ourselves when you got there. This is the same thing, we're just doing it faster. It's okay if it didn't do it. If it failed, communications are out. You can still open these devices in the field, do these things that you've always done. So just to recap, our system is about 45 to 60 seconds. We got 42 feeders, 39 of them have FLISR, and the reason there's 3 that don't is they don't have a 2-way feed. They're kind of fringe feeders. I'd love to have somewhere to feed them from, but I don't have anything on the other side. We got about 120 devices on the network, and we're getting about 30 to 50 events a year to automate with. The system map updates, if anybody here has a DAS map, sometimes that can take time. Once you get it smooth and you figure out what to look for, you know what's happening. But when you're adding 20 devices a year, DAS map updates can be time consuming to make sure all your points move over, your functionality's there. These devices do need field maintenance. You got to ride by, check them out. We've covered those up for animal cover. You got to make sure everything's still covered up. You got to make sure there's no squirrel building a nest in some animal guard. And then you may have database updates once you add new points, or if you had an update in your settings year 3 that you didn't know you needed until you had 2 years of experience of running a system. Well, you got to come back in the database and update those old stations as well. You got to keep training employees. If they don't see it and they don't use it, they forget it. So if this part of what this has given us is the ability to backfeed a substation outage, but that one's done manually right now. But our operators have to know how to identify substations out. It's okay to backfeed. Do I have the correct devices are showing open? There's no fault flags. Why didn't FDIR backfeed? Why didn't FLISR backfeed this? They have to identify, what should it backfeed, what can't it backfeed, and we usually get, 1 or 2 of those big substation outages a year, and if you're not practicing it, preparing them, they're going to miss the opportunity to save all that time of an outage. When you have a standard setup, it's easier to administer, it's easier to train on, it's easier to pull reports. if you can do anything when you're doing this, a favor for yourself is to have that easy copy-paste settings for each device. Maybe your time curves change, but everything else is pretty consistent. And then, you know, we do have failures. The system is not perfect. Most of our failures, we've had about 5% so far. Most of them have been communications are out. You got a relay with no communications. I can't tell you if it's locked out. I can't tell you if it's SAIDI fault. I can't even control it. We have had some DAS map updates. When you're doing 20, 25 devices a year, you're replacing some old hydraulic reclosers that may have been overloaded if you were to backfeed on them with a SCADA controlled device. Well, if you don't pull that off of the map and the map still sees it, it's going to go through and say, well, you're going to overload this recloser, we can't do it. So you got to keep your map, you got to remember what's happening on that map. And lastly, you may have communications, but maybe you had your timing off just a little bit. So you miss an opportunity to backfeed. These two here, they'll eliminate themselves over time. You'll find them, you'll fix them. Communications, it's gain a chance. Hopefully you have communications or you can make it more robust. But I don't know if you'll have any questions on that. Our future plans, we're hoping to do some single phase backfeeding in FLISR. We may have to push that up to 2024. We're looking to do some substation backfeeding in FLISR as well. That's big SAIDI savings. We're looking to add in some fault circuit indicators to bring that information in to some midpoints so we can send a crew right to the middle of the quarter point in the feeder. Open some switches, we can backfeed, get another quarter of that feeder back on, depending on if the fault indicator's lit up or not. Volt-var optimization, we're currently working on that. And then if there's any integration with solar diesel network, we can start putting these resources in with DERMS, eliminating someone having to make a decision, looking at data. The system just knows, here's what I'm seeing, here's the decision we're going to make. So I don't know if y'all have questions for me. I have some questions for y'all. I don't know who else is putting in a system-wide automation program. Nobody. All right. Rob, get busy. Has anybody implemented a localized automation scheme? So you got some experience. Those things, they can be finicky. Once you get them working, you just leave them there. You don't worry about it, right? Until they break, and then you worry about it again. This is very similar to that, except for all of your logic is in your SCADA head end. So you're not having to decide when to switch. You set up a recloser just like any SCADA recloser. You put your curves, you build your open closers. The only thing you add different is a fault flag that indicates you saw a current over a certain limit. SCADA makes the decision. SCADA sends the commands to close, sends commands to open. Sometimes those localized schemes can get pretty hairy pretty quick. And then most of the questions we get are these three. How do your linemen and control center respond? At first, our linemen were scared to death. They said, there's no way we're going to get out there and this computer's going to backfeed us, backfeed this line we're working on. And we reminded them that this is in 45 seconds, so you won't be out there that fast. And if you go there and the power's off, that's where you need to be, fixing the problem. You're not going to go where the power's been turned back on. So that's something well, it depends on your technology you've got. We're currently working with some stuff with MillSoft to be able to show some of those temp operations with a field map. We started this in 2017, so here we are. We're still building it 5 years later, but I think the technology hasn't caught up. I think that's where the technology needs to be. But a lot of it comes down to if the linemen remember, hey, when you get there, test for voltage, put your grounds on, you're good. There's a reason you have all these tools. Our control center staff, at first, when we first put these devices in the field before FLISR was live, some of the questions were, do I have to do these switching opens and closes? Yeah, hey, we've got all the data there, we've got these devices sitting there, you have to open, close, move, load around, get people back on. I think that the biggest thing to them was we always waited for the linemen to tell us what they saw. Well, now SCADA is telling you what it's seeing. You just have to learn to trust what SCADA is saying hey, this saw the fault, this device locked out, I can turn on this area back here in this area, trusting what SCADA has. And it just took some experience, took some time. They're getting more comfortable, took a lot of training. And then after it became automated, them seeing it do it, it's helped our culture with switching a lot. You know, FLISR's doing this, we can do this too. Can FLISR be deployed if all devices are not automated? That it can be. We did this in sections. So our first section was deployed as we were deploying relays in the middle. They weren't on FLISR yet. We hadn't tested them, so the system wasn't controlling them until you go in there and turn that feeder on. You can decide each feeder, and I think even in some of the newer versions, you can decide if it's manual or auto on each feeder, or even a storm mode. And that's the last question is, do you turn it off during a major storm? And so far we haven't. We've just kind of let it run, and it's been really fun to watch it while you're sitting there. Your crews can't get in the bucket. The winds are too strong. You'll see a feeder lock out, see a midpoint open, a two-way feed close in. You know half your feeder just got turned back on. So it's been pretty rewarding. I don't know if y'all have any questions.
Staffing, how did ADMS change your staffing? Do you have a dedicated resource for it? SCADA techs or field resources?
Yeah, so for us it depends on the level of the person you have. If you're the only person that programs relays, well, you just added 120 out in the field that you got to drive to. If you're the only person that knows how to do radios, we just added 120 in the field that you got to drive to and work and troubleshoot. So really the staffing says, hey, I need this more technical knowledge to spread some of this work around, or we're going to wear somebody out. So if you already have that staff and you're covered, all your substations, everything's working good, adding 120 devices may not be many for somebody. For us, that was probably double what we had in the past.
Yeah, we added, remember Jody was a new admin?
That's right, yeah, we had a dedicated lineman into our engineering department. So I don't know how somebody else's structures are, but as we pulled that dedicated resource in, it allowed us to get up into the high voltage area, work on these devices without scheduling time from a crew or pulling somebody off of a service crew to come and, hey, what do you want me to take off of this device? This device, I've never worked on this device before. This is a SCADA device. We don't mess with these. So it's a big thing looking at your culture of your company. You know, the reclosers scare some people. Yeah, substations scare some people. So it's getting comfortable with things. I think you had one.
Yeah, I got a question. Do you guys have anything within your algorithm that uses to double check to make sure devices operate as they expected to?
Yeah, so that's,
Make sure it actually did restore, that the load actually was restored, and then as well as maybe when you're
there's a recloser switch delay. We send a signal out, well, FLISR will not advance to the next step until it sees the device report back closed or open. I think that's also in the switch plan. It may send a command, and it waits. Oh, status came back. It does say open and closed. So you have to map all that into FLISR. It needs to know the command to open and closed, the control point, but there's also the status point. So it will not advance. It'll stop. If one doesn't come back and say it closed in or didn't open, it stops. Plan terminated, recloser failure.
For the restoration of expected load, though, you know, in case you had a three-phase device with only, for whatever reason, another mechanical failure, only two of the phases closed in, and so that third phase didn't really pick up the load of the device.
So FLISR won't really look at that, but our relay in the field, you can program them. We actually decided to go with a triple single. So we're doing three-phase, single-phase tripping and also single-phase lockout. So it'll indicate, hey, we sent the trip, we expected all three, only two opened. We get an alarm and it may drive the other phase to lockout. But if it's under a fault condition, one phase can trip, lockout, because we're so rural, we're mostly residential, it doesn't make a lot of sense to drop all three phases if we had the ability to just drop one. We didn't have a lot of imbalance issues, but you can program it to look for all these different indicators, and you also have to remember there's a mixture now, because you're not doing localized control. There's what does your overall entire system need to do, what does this area, what does this single relay need to govern and watch for?
You guys' models that start at the feeder head end breaker then? And so
As far as,
your impedance model.
Yeah.
So, is there any, I guess, thoughts or whatever on what happens if the substation itself is set at normally, that is normally maybe a good source that compares well with this other substation next to it, but for whatever reason or another, they're fed differently, and then the power flows are going to be different. There's certain types of tie-ins.
yeah. So FLISR actually has a topology model that's real time. It's going to look and say, what is the system right now? It'll do automation, it'll backfeed, now you've got a feeder and a half on a feeder. Oh, another fault comes in, but let's say you have a third tie. That piece will walk out, it's going to say, what was the system at that point? Let's backfeed it again. Some of the stuff you put in is just your transformer impedances, your transformer max loading. Those type of decisions, you put in the limits, and the system's topology can change and move around, and it restudies it every time that it has a decision to make. It'll rerun that decision.
But you're currently not monitoring the upstream transmission systems themselves.
We're not, yeah. We just hope you guys are ready for it.
A couple questions on your indices. Your major event day, is that more than 90% of your coverage area? Or what do you
A major event day is defined by IEEE standard. So there's an equation that looks at your 5-year running SAIDI average. And so and it creates an annual threshold basically. Ours, I think, when we started this was up around 35 minutes in one day would be considered a major event day. And now I think we're down in the low 20s because, our SAIDI has been coming down. So
And momentaries, do you not count momentaries?
we do not
Okay,
do any
what-
Mayfie work, yeah.
And what is your momentary, 1 minute, 5 minutes?
Our reclose cycle half second on what we call fast trip. We're set up for fuse saving. And then I think we have a 5 and a 10-second reclose and then lockout. So
Yeah, and then our outage is momentary is defined 5 minutes because we're
that's-
electric co-op, yeah.
that's IEEE standard of 5 minute. Anything less than 5 minutes is considered momentary.
Yeah, I think some of the IOUs might fall underneath 1 minute momentary definition.
Yeah.
But either way, we're backfeeding these in 45 seconds, so.
That's good, but then you have to possibly wait another 45 seconds for the next one, because you say.
Well, yeah, if you had two happen at one time. Well, they can be in different areas. It's just, if one feeder has to go all the way through a full backfeed, then you have another fault on that same feeder, but I could have two faults happening on our system, two different feeders, and they'll backfeed both of them separately.
Do you have any issues keeping all your different models in sync between like OMS and ADMS? Is that the whole?
Yeah, so keeping the models in sync,
They're never truly in sync 100% of the time.
yeah, it's a challenge. I mean,
No. When you're looking
It's a
at
challenge.
customers, no.
yeah, I think you have to look at the use case for the system you're using. Our staking map, where we're doing all of our builds, that's updated as soon as the construction crew says they're done. Our OMS map may be a month or 2 months behind getting meters on the map from those jobs that are being built. This system here, you can go 3 months, you can go 10 months. If you're not adding a bunch of three-phase changes, you're not adding a bunch of devices, it's going to still make the same decisions. And if you're not adding a bunch of load, that topology load change is not really going to make a big difference. So it's really how fast are you growing, and
Feeder backbone.
that's right.
Yeah, basically, yeah.
And if you go add a bunch of load on one of those feeders, you may want to update it. But also, in Florida, you don't want to go updating things mid-August. You wait till October's over, you update it, you make sure it's good. Maybe you do it again in February, and then in May, you hold tight and you wait for the storms to roll on through. Oh, if I send a command, we're like within 1 second. It's reporting back, tell you it's closed or open. Yeah, it's pretty quick. I mean, click, it's open.
And that's over radio?
It's over both, actually. Our cellular is maybe a second and a half. It's pretty quick, but then our 900 megahertz it's faster. I mean, I've never really seen a big delay in anything we're doing.
Thanks, guys.
Yeah, thank y'all.
Yep.